Hi everyone, welcome back. Today we're starting with the announcement that Kevin has. So Kevin, please go ahead, and then we'll start the webinar.
Great. Well, thanks Bunyamin for letting me announce this just for a minute. Many of you might have received an email about this conference that we're going to be having October 3rd. It's called VOTCAM, the Virginia Operator Theory and Complex Analysis Meeting. You can see the poster that my colleague Stephen Hardy made. This is a ripoff. No, it's an improvement of an Elvis poster from 1959. That's where the number 50 million comes in. I think you should just stare and take in how amazing a job he did on this poster. So this is a one-day meeting, October 3rd. In order to register for the meeting, of course, it's on Zoom. It's, Bunyamin, could you put it? It's votcam.wordpress.com. Does that appear in the chat? Votcam.wordpress.com.
All right, let me do it again.
Yeah.
Okay. All right.
I can't somehow see how to do it.
All right.
If you go there, you can find more information about the meeting, and you can put your name and email on a registry, and then I will send you the link for how to register that day. We have 5 speakers. You can see the speakers: Lisa Clark, Noid Rancor, Joseph Eisner, Adrian Iona, Gideon Sheckman, and Alan Sola. So a mixture of people in operator algebras, operator theory, Banach space theory. We've been doing this conference since 1992 annually, and many people have spoken. This year, we have also Bill Johnson and Masamichi Takasaki will be doing a panel talking about their life in mathematics. I'm very excited about that. Thank you for Bill for agreeing to that. So that's all I have to say. If you're interested, you could also email me or just go on the website. So thank you, Bunyamin.
All right, thank you so much, Kevin. Are we required to dress up Elvis when we join, or is it?
No, I forgot to tell you that. That's a requirement.
Okay. All right. So with that, so let's get started with our webinar. Today, we are very pleased to have Marie Angelica Tursi from University of Illinois Urbana-Champaign. She is speaking on separable universal homogeneous Banach lattice. Marie, please go ahead.
All right. Thank you, Bunyamin, for inviting me. So yes, I'll be talking about a separable universal homogeneous Banach lattice that I constructed. All right, so some motivations. So many of us are familiar with the Gramcko-Tursi space. We'll call it script G here. It's the unique isometrically universal separable Banach space with the following property: that for all isometric embeddings f from A to G and g from lowercase g from A to B, with A and B both finite dimensional spaces, you have some h such that h of g is equal to f, and h has arbitrarily small distortion. So one thing we can do is maybe we want h to be isometric, but if we do that, we're going to have to weaken the commutativity of our diagram to just an approximation. So you have for any epsilon, you can make h of g minus f have a norm less than epsilon. And one thing is that it can be constructed as an inductive limit of L infinity n spaces. And these L infinity n spaces are special in that they make up the injective finite dimensional Banach spaces. So there's some relation between, there's a relation here between these injective spaces and the Gramcko-Tursi space. So homogeneity, trying to find homogeneous spaces, this is still an active area of research. There's a classical result with the Hilbert space that you can extend any L2 space into some, with 2 embeddings into it, into some automorphism on L2. But recently we have approximately homogeneous objects, so you can have almost commutativity. And Lupini did this in an advanced paper for various kinds of classes, for example, function systems, P multinorm spaces, and MQ spaces. And he used some he used injective objects with some of the metric Fraïssé machinery that we'll be talking about later in this talk. And in another advanced paper, we have, it was shown that you have LP 01 and a homogeneous AM space, and this is for Banach lattices in particular. It was shown you can construct homogeneous spaces especially for certain classes of spaces. With the atomless LP, you can use any LP finite dimensional, and your embeddings are lattice embeddings instead of just linear embeddings. And the same thing for this homogeneous AM space. You can your embeddings are now lattice embeddings for finite dimensional AM spaces. And I also want to mention non-separable versions here. Spaces of universal disposition have also this kind of homogeneity property, but you have full commutativity and for full embeddings, not just, but then you sacrifice stability. So I'll mention in particular Banach spaces of universal disposition. And this was with Aviles and Sanchez back in 2011. And then very recently, there was also a Banach lattice of universal disposition that was constructed. So just to show that there's a lot of very recent research going into these homogeneous spaces. All right. Oh. How do I get out of here? It's asking me to. Okay. So just for a brief review, do you guys see this jump to page, by the way? Did that pop up in the screen or?
I do, yeah. I don't know how.
Let me
just do escape maybe, yeah. Okay.
Yeah, that's what I'm doing now.
Okay.
Okay. So just a brief review. So these min and max functions that behave very nicely with the addition and scalar multiplication operations, and they also work well with with the norm, which has it's a lattice norm, so it works well with the order. So some common examples are C of K spaces and LP spaces. But now let's now go more into some of the preliminary information for the logic of metric structures, which we're going to use to construct our homogeneous separable lattice. So suppose you have script L, a collection of symbols, and then we'll let script A with the associated metric space A be an L structure if for every predicate symbol R, there is some continuous function from A to its arity to the real numbers. For example, if you have metric spaces, a predicate symbol is distance, right? And every metric space has some distance function, and we use D for it. And then for your, we also have, for every function symbol in your language, there is some continuous function from A of n to A itself. So for example, if you're dealing with Banach spaces, your language is addition and scalar multiplication by real numbers. And because every Banach space, you have some particular way to talk about addition that's specific to the space, or scalar multiplication. With Banach lattices, you also have these min and max functions. You can, if you want, restrict what your scalar multiplication is to just Q. So there is some flexibility allowed here, but the idea is that your structure has a way to take these symbols and interpret it for its particular, for the particular space. But throughout, we'll just refer to structures by their underlying sets. So we don't need to use the script, whatever, we can just say X in our case. So then a map, phi from x to y between L structures is an embedding if for all function if phi preserves your function symbols and your relation symbols. So for Banach lattices, these are lattice embeddings. So these are functions that preserve your addition, scalar multiplication, your min and max symbols as well. And it's enough to show that a map is a lattice embedding. It's actually just enough to show that it's linear, it's positive, and it preserves disjointness. And also to show that it's an embedding, you just need to show that it preserves norm. But we'll extend that a little bit for here because we'll deal with a bit of distortion. So we say that a map phi from x to y between lattices is a C embedding if it's a lattice homomorphism and it has a distortion that's bounded by C. So every x, for all x and x, the norm of phi of x is between 1 over C norm of x and then C of norm of x. And if phi is also surjective, we'll just, since we're mostly dealing with lattices, it's short for just, C lattice isometry, but we'll just call it an isometry here. Also, if C is equal to 1, we just drop the C and just say they're embeddings and isometries. And at least with the embedding cases, it aligns with the continuous logic definition of an embedding here. We'll also work with specific types of structures. So if you have a set A that's that's a subset of some lattice X, or just, well, any L structure specifically here, then we'll denote by bracket A the substructure that is generated by the elements in A. So this is going to be the smallest closed subset containing A that is also closed under the functions. And obviously the relation, the predicate symbols are also preserved throughout, but it's generated by the function symbols. So if A is finite and A generates all of X, then we say that X is finitely generated. So with Banach spaces, these are your finite dimensional spaces. With Banach lattices, there's a much larger range of lattices that are finitely generated, but they're not finite dimensional. So for example, any LP space, the continuous functions on the Cantor set, and then also continuous functions from the Cantor set into L1. And I mention this space because it's a separable universal Banach lattice, so that any separable lattice isometrically embeds into it. And this was constructed by, I mentioned the space also because it's going to be used throughout this talk. It was constructed by Denny Long, Leili, and Timur and I in a recent paper. So we'll also be using this kind of metric that I'll describe now. So let script K be a collection of finitely generated L structures. For if you have some tuples bar A and bar B, they could be in some ambient space. We let the distance between the tuples, assuming they're of the same length, equal to the max of the distance of corresponding elements in the tuple. And then we also introduce this, this kind of metric-like measurement. We say D of K, A and B, is going to be the infimum of some ambient space. So one thing about these tuples is that we want to think of them not just as just tuples of finite elements, but also in terms of the structure they generate. And so that's why we're including this additional metric, and assuming that they can be embedded into some ambient space C. And these embeddings are in fact embeddings from the structures generated by A and B into this C. So we say that such a class K of finitely generated structures is Fraïssé if it satisfies the following properties. First, if it has the hereditary property, That means that K is closed under finitely generated substructures. We say that it has the joint embedding property if any two structures in K embed into a third structure in K. We also want the near amalgamation property, and that means that for any structures, finitely generated structures A, B1, and B2, with big A generated by some tuple A, and if you have some embeddings from A into each BI, for all epsilon greater than 0, there is some finitely generated C and K, such that, and embeddings from each BI into C, such that you have an almost commutativity of your diagram along your tuple. If we can get full commutativity, we'll just say that script K has the amalgamation property, and we'll initialize that with AP. In addition, your K, if it's Fraïssé, it also has to have the continuity property, which means that every symbol in your language L is continuous in K. So for function symbols, if you take the map from A, bar A, comma, bar B, to A, comma, B, comma, the function on A. So this is a function that takes in tuples of length A, and you get something like that. This map is continuous with respect to this, this D of K. And a similar thing for predicate symbols. So to give a specific example of this, if you're dealing with Banach spaces and you take the function of addition, the addition function has this modulus of continuity that's independent of the space you're working with. So, so it's specific to the symbol itself, and then it can be applied to any structure that's a Banach space. So then we can say that this, the addition operator for Banach spaces is continuous in this way. Also with last requirement is that K has the Polish property, which means that your D of K is separable and complete in K of n, which is the K structures generated by n many elements. One thing to mention is that your generation doesn't have to be minimal. It could be, you could have tuples that where two elements generate a third in the same tuple. But the point is that you can have some countable dense collection of tuples and that it's complete. And so one thing to note is that this D of K functions like a metric under certain conditions. So if you have the joint embedding property, D of K is defined for all of K. And if you have the near amalgamation property, then the triangle inequality holds for D of K. And finally, if you have the continuity property, then D of K of A and B is equal to 0 if and only if you have some surjective embedding, so a bijection that preserves all your function symbols from the structures generated by A to B with phi of A equal to B. So this works like a distance in your class K. And where your tuples are represented, represent spaces up to isometry with an additional fixed point. So this was by Banach. So if you have a Fraïssé class, as described just recently, then there exists a unique separable structure M with the following properties. One, M is approximately ultra-homogeneous. So for all embeddings from some finitely generated structure A into M, any two pairs of embeddings, and for all epsilon greater than 0, there exists an automorphism from M to M such that the distance of phi of F of A and G is less than epsilon. So you can take any two embeddings, and then you can get some automorphism that almost extends, that approximately extends one of these embeddings. The second requirement is, the second property is that the class of finitely generated substructures of M is K. So that means that your M is going to be universal for your structures in K, and it also has this ultra-homogeneity property. So some examples that we're familiar with are finite metric spaces. Those form a Fraïssé class, and then the Urysohn space. Finite dimensional Banach spaces all form a Fraïssé class, and their Fraïssé limit, which is this separable structure, is a Gouraud space. So remember, in the first slide, I mentioned this other kind of homogeneity where you have almost commutativity. That's because the Gouraud space is a Fraïssé limit. And then you have LP lattices, and the Fraïssé limit is the atomless LP space. So for the rest of this talk, I'll just let K be my class of finitely generated Banach lattices. The main result is that this class is in fact a Fraïssé class as well. And then that there exists an isometrically universal separable Banach lattice script BL that is approximately ultra homogeneous. So I'm going to give a basic description of the proof here. So first of all, Banach lattices clearly have the joint embedding property and the hereditary property and the continuity property. For joint embedding, you can just take any two lattices and do a sum of those lattices, and you get another finitely generated lattice. Hereditary property follows from the very definition of our class. It's just finitely generated lattices. And so a sublattice that's finitely generated is still a lattice that's finitely generated. And for the continuity property, this follows from the fact that the lattice operations themselves have moduli of continuity that's independent of your space. So we can show that the continuity property follows from that. The main challenge was to show that K has the amalgamation property. So just to acknowledge here that that very recently also, Aviles and Fraïssé also proved that Banach lattices have the amalgamation property using free lattice constructions. And this result was proven independently from the paper that I recently submitted. So just to acknowledge that, and also to encourage you guys to read that paper as well. It's pretty good. And the last property is the Polish property. This follows from the joint embedding property and the amalgamation property, and the existence of a universal separable lattice. So if you have a universal separable lattice, you can just take some countable dense set and then take all the finite tuples from that countable dense set, and that will give you something that is dense in your metric D of K. And then for completion, what you can do is if you have some sort of DK Cauchy sequence of tuples, you can then use the joint embedding property and the amalgamation property several times to get some big, large ambient space that contains all of your lattices. And then there's going to be some limit of your tuples, and that itself, it can be generate some lattice as well. So you have a complete metric for D of K. So the main thing was to show that, so we're going to give a proof of the amalgamation property for separable lattices, but this proof will also involve an additional subclass that can say some very interesting things about script BL. So we'll look specifically at this class K prime of K, which is the class of sublattices of L infinity M, L1, N spaces. So for any M and N. And so in order to characterize this, I'll just introduce some quick definitions here. So a subset A of X is solid if for all X in A, and whenever the modulus of Y is less than or equal to the modulus of X, then Y is also an A. So these are sets that are closed inwards with your downward order. A solid convex whole of A is the smallest solid convex set containing A. If we want it to be closed, we'll say the closed solid convex whole, and that is the closed solid convex set containing A. And then finally, we also have an analog of extreme points. So an ordered extreme point of A is some little a of big A, such that for all x and y of A, if we have little a less than or equal to x plus y over 2, or any sort of linear combination tx plus 1 minus ty with t between 0 and 1, then x is equal to a and equal to y, right? So these notions are basically lattice analogs of what we know about convex hulls and extreme points. And if you want more information on that and some of the various results you can do with these, there was a paper that Timur and I recently had published, and it's in a volume dedicated to Viktor Lomonosov. So there we talk about these analogs of extreme points and convex hulls. But we'll be using some of those, we use some of those tools to characterize some of the results in this paper as well. So back to this K of prime, the K of prime then we can describe geometrically. So it turns out that if you have a finite dimensionalized x, x being in K prime is equivalent to saying that it has finitely many extreme points, or the dual has finitely many extreme points, or that it has finitely many order extreme points. And so visually, what this looks like is that if you have some x that's in K, its unit ball is polyhedral. And so given that, that can give a little bit of intuition for why this also follows. If you have x a finite dimensional Banach lattice, then for all c greater than 1, there is some c embedding from x into an L infinity m L1 m space for some m with big M equal to the dimension of x. If x has finitely many ordered extreme points, then we get then this is based on this was just a specific statement from the previous lemma, but you can embed it isometrically. And notice that if you have a C embedding, then your image is some element in K prime, and it's so the idea is that you have some unit ball, you can approximate it by taking a bunch of points on X, and then taking the solid convex hull. That thing is going to be in K prime, and it also approximates your unit ball in X. So based on this, we can now prove an amalgamation property for K prime. So if you have embeddings from Fj from E to big Fj, and these Fj's are in K prime, and your little Fj's are C embeddings with C greater than or equal to 1, then there is some G in K prime and C embeddings from each Fj into G, such that you have commutativity in your associated diagram. So in particular, since I said C is greater than or equal to 1, if you have C equal to 1, then you've shown the amalgamation property for K prime. So I'll give a quick sketch of that. So assume that F1 and F2 are both just L infinity and L1 M spaces, and we can just expand whatever F1 and F2 are by just mapping it into it, mapping each into such space. We're going to let U K of J be the jth atom in your kth L1 M row for F1. And so you can think of your L infinity L1 space as these L1 rows, and they're added with an infinity norm, with an infinity sum n times, right? And the same thing with F2, we're going to just let Vk of J be the jth atom in the kth L1M norm. So we let E be the described in terms of its atoms, and obviously these atoms generate E. And we're going to we'll describe very briefly some of the notation here. Note that you can take any row and you look at which atoms support your say F of 1 of E1, and we're going to let F1 IK be all of the J's such that your UK of J supports F1 of EI. And the same thing with F2 of IK. Then given that, we can describe any pair of embeddings in the form here. So F1 of EI is mapped to the sum over all rows K, and for all J in F1 of IK, these weights added to your atoms UKJ. So for example, if you look at my little table on the right-hand side, F1 is mapping E1 to these atoms along all of these rows, and the same thing with F2. So then, given this kind of construction here, we're going to let F prime of M be the ideal. So these are lattices that are closed under downward order. We'll let F prime of M be the ideal generated by the image of each FME for M equal to 1 or 2. So in the bottom case, there's like all these gray atoms that are not marked. These are not in F prime of 2, for example. So now we're going to construct our H, G1, and G2. So we'll define these maps. We'll define G1 from F1 to the tensor product of F1 prime and F2 prime. And then we're going to just add copies of F1 and F2. And for every atom UKJ that is supported by some F1 of IK, some F1 of I, we're going to let G1 of this UKJ equal to UKJ tensored by F2 of EI. But if UKJ is not supported by any atom, any F1 of EI, then we'll just let G1 of UKJ equal to UKJ in that additional copy of F1 that we added. And the same thing with G2, if VKJ is supported by some F2 EI, then we let G2 of VKJ equal to F1 EI tensored VKJ. And but if VKJ is not an F prime 2, then we'll just map it to itself under the additional copy of F2. And this will generate some maps over the whole space. So one thing to note is that you're mapping atoms to disjoint elements that are positive. So your map is positive, it maps disjoint elements to disjoint elements, and then you can generate a linear map based on this. So these J1s, the G1 and G2 are lattice homomorphisms over this vector lattice H. So what we're missing now is the norm that we're going to ascribe to H. And so your H will be the lattice specifically generated by the images of G1 and G2. And we let the unit ball B of H be the closed solid convex hole of the union of the images of the unit balls of F1 and F2. So one thing to note is that F1 and F2 have finitely many order, the unit balls have finitely many order extreme points since they are in K. So B of H will also have finitely many order extreme points since lattice homomorphisms preserve extreme points. So your H is also going to be in K prime. And it's a very technical proof to show that each GI is a C embedding, but it is so under this particular, when we give this norm to H. So we can then expand to arbitrary finite dimensional lattices and show that there's an approximate amalgamation property for all C greater than or equal to 1. And if you have E, F1, and F2 finite dimensional lattices, and you have C embeddings E into F1 and E into F2, then for all epsilon greater than 0, there is some lattice G, and we can even add that this G is in K prime, and some C plus epsilon embeddings from F1 and F2 into G. such that you have G1 of F1 equal to G2 of F2. And we can just illustrate this pretty briefly here. So you take, you start with your E and pair of embeddings, and then we can embed each Fj into some L infinity ML1 n space with a 1 plus delta embedding for delta arbitrarily small. Then we'll use our theorem 7, which was our amalgamation property for K prime, to get some C times 1 plus delta embeddings into G. And then we just let G1 and G2 be the composition of the embeddings that we had just constructed. And we can let delta be arbitrarily small so that you have C times, I think, 1 plus delta squared less than C plus epsilon. And so now your G1 and G2 are C plus epsilon embeddings. So we are using finite dimensional lattices, but we need to branch upwards to finitely generated lattices. So the key concept here that bridges these two is finite branchability. So a separable lattice, necessarily separable lattice, as we'll see, is finitely branchable if it's the inductive limit of a sequence of finite dimensional lattices. So some examples are LP, C of delta, and then also our universal separable lattice is in fact finitely branchable. A counterexample is the continuous functions on the unit interval. So one thing about finitely branchable lattices is that they are finitely generated, and in fact can be generated by 2 elements. So now you have a good sense of some of the breadth that can of these branchable lattices. But of course, not every branchable lattice is finitely branchable. Not every lattice is finitely branchable, but for every separable lattice X, there exists some finitely branchable lattice F that is inside of your double dual. So that's going to be important for later. So how do these work? Well, generalizing a little bit, if you have a lattice and you have alpha a limit ordinal, and suppose that you have decreasing net, this alpha net of lattices such that their union is dense in E, we can then let script E be a lattice of alpha convergent nets in E, and we can equip E with the sup norm and take E0 to be the ideal of script E. So script E0 to be the ideal of script E of alpha nets converging to 0. So basically we can show that our E is lattice isometric to the quotient of E by E0, script E0. So the idea is that you're thinking of E as a bunch of, in terms of the sequences that converge to points in E. And if your E is finitely branchable, then we just let alpha be omega, and then let En be a sequence of finite dimensional lattices. Sorry, I'm in Calc 3, so some of the Calc 3 information is seeping in here. But you let En be finite dimensional lattices, and you have an increasing sequence. So now we can describe E, a finitely branchable lattice, in terms of sequences of elements in finite dimensional lattices. So one thing about this is that if we have more generally a increasing sequence of lattices whose union is dense in E, then if I have any finite dimensional lattice, sublattice of E, then I can approximate it by some lattice in some E of n. So how do we work from embeddings between finitely branchable lattices to finite dimensional lattices? If we take E and A, finitely branchable, and then suppose that phi of E to A is an embedding, we take En and An to be sequences that whose inductive limit is E. And then for all epsilon greater than 0, there is some strictly increasing sequence Kn in the natural numbers, and 1 plus epsilon, there's a 1 plus epsilon embedding phi prime from script E to script A. And here script A I'm thinking of as it doesn't have to just be sequences in each AN, and we can take a subsequence and then generate script A like that. So you have some phi prime generated by a sequence of maps phi n E of n to a k of n. So I'm letting my script A be generated by the a k of n's, such that you have this kind of commutativity in your diagram. And also for each n, my phi of n is itself a 1 plus epsilon over 2n embedding. So generally, intuitively, the idea is this: I have my embedding, and then I can approximately describe this embedding by taking a sequence of embeddings between finite dimensional lattices, and then looking at the sequences of elements that is formed by that. So this will, in effect, reduce a problem involving infinite dimensional lattices to finite dimensional lattices. So now we prove the theorem for so you have E, A1, and A2 that are separable Banach lattices. We let F1 from E to A1 and F2, E to A2 be embeddings. Then there exists a separable Banach lattice G and embeddings from G1 and G2 into G, so that you have commutativity in your associated diagram. And then you can use a similar approach to prove amalgamation inductively over lattices of given density character. So that results in an amalgamation property for lattices in general with independent proofs. So basically you have E, A1, and A2 Banach lattices, arbitrary Banach lattices, and you have some embeddings. Then there is some lattice G and isometric embeddings into G, so that your associated diagram commutes. So in the case for separable lattices, you can start, if you start with E and your associated embeddings, you can extend your maps, your embeddings, into embeddings with between finitely branchable lattices. So go into your double dual, and you have your F1 and F2 double stars. Find some finitely branchable lattice E prime inside of your double dual, and then you can extend your A's to finitely branchable lattices where your F1 and F2 embed into those. So then we can now, okay, there. So now we can use our lemma to lift into these 1 plus epsilon embeddings between sequences within your lattices. And remember that these F'1 and F'2 are themselves sequences of embeddings between finite dimensional lattices. And so what we can do then is amalgamate every finite dimensional, every corresponding pair of embeddings over a finite dimensional lattice into some G of n with 1 plus epsilon over 2 n embeddings Gi of n, so that you have commutativity for each individual component. And then you let G prime of I be the embedding from script A prime of I into this, the product of G of n's, with G prime of I equal to the sequence of the Gi n's. And then let script G be the lattice generated by both G prime I, A prime I's. And then you equip this G prime with that suit norm along the components of your sequence. So now we're going to let G be equal to the quotient of G over script G over script G0, which is your sequence of your null sequences. And then we can let GI be the composition of your quotient, your G prime I, and then the inverse of the quotient for each A prime I. And this turns out to be well defined. And it preserves the lattice and Banach space operations. and it also preserves the norm. And so your K, and also if we want our G to be separable and insured, we can just limit G to the lattice generated by the images of your GIs. And if we want to make sure it's finitely generated, we can just embed it into the universal separable space, because that's generated by only 2 elements. So our class K has the amalgamation property, and it is thus a Fraïssé class, which means that we now have our isometrically universal, separable, approximately ultra-homogeneous lattice BL. So now we're going to look into some of the properties of BL. In particular, we're going to work with this K prime that we had been using. So recall that 2 of the properties of Fraïssé classes are the continuity property and the Polish property. But we can also weaken this a little bit and instead talk about the Cauchy continuity property and the weak Polish property. So instead of it being every symbol being continuous, it should be Cauchy continuous. So you take a Cauchy's DK Cauchy sequence, and it gets you another DK Cauchy sequence, but it need not be well defined in that sense. So it doesn't have to actually converge to some element. And then the weak Polish property, your D of K is separable, but not necessarily complete in your K event. So if you have a class of finitely generated structures, one second. All right, we're gonna have a child here. So if you have a class of finitely generated structures with the hereditary property, joint embedding property, and the near amalgamation property, but you have these weakened properties instead, then it's an incomplete Fraïssé class and admits a limit of its completion. So for example, with LP lattices, the finite dimensional LP spaces actually are an incomplete Fraïssé class in your LP spaces. But what's interesting here is that the class K prime is an incomplete Fraïssé class, and its completion is K itself. So you can approximate according to this DK metric any finitely generated lattice by some lattice in K prime. And in particular, you can have a Fraïssé metric, K prime, where it's defined, but you can only embed into elements of K prime instead of any K. And this metric, in fact, coincides with DK. So I like to think of these K prime lattices as a sort of, they provide a sort of skeleton for BL and for your K. So one result of that is that you can construct BL as an inductive limit of L infinity M L1N spaces. So remember, I mentioned earlier that an incomplete Fraïssé class admits of a unique Fraïssé limit of its completion, but we can tweak the machinery used by Banach to show that BL is constructed only using lattices of K prime. So that's how we show this. But a result is that if you can take an inductive limit of L infinity M and L1N spaces and get BL, then we've shown that BL is finitely branchable, and it's also finitely generated as a result. So, that's how these K primes fit in here. So I'm going to finish with an alternate description of homogeneity coming from functional analysis, and then use some of the tools here to give an explicit construction of BL. So lattice X is of approximately universal disposition for a class C with lattices defined by finitely many elements, and I'm going to keep that a little bit ambiguous here for now. if for all embeddings f a to x and g a to b, with a and c defined by some tuple a and b and c, and for all epsilon greater than 0, there is some 1 plus epsilon embedding h from b to x that almost extends your f. So when I mentioned defined by finitely many elements, with lattices, we now have at least 2 ways of doing that. One could be finitely generated lattices, and the other one is finite dimensional lattices. There we go. There we go. So now with finitely generated lattices, note that with approximately universal disposition, there is a relaxation of your extending embedding to some 1 plus epsilon, rather than it being a full embedding. But with finitely generated lattices, that relaxation is just semantic. Any separable Banach lattice of approximately universal disposition for finitely generated lattices is already isometric to BL. And if you have a finitely branchable lattice of approximately universal disposition for finite dimensional lattices, this is also isometric to BL. And here, for the second statement, the finite branchability is an important part of the proof. So it's actually open whether you can have a non-finitely branchable lattice of approximately universal disposition for finite dimensional lattices. But at least now we can, when we do a construction, we don't have to have full isometries. We can use a little bit of a distortion and still get something isometric to BL. So that's what we're going to do. So we'll, so what's my time, Bunyamin?
Right around there. You can use 2-3 minutes.
Okay. All right. I can do that. So we'll use this lemma. Basically, if you have a C embedding from A to X, then there is a C equivalent renorming of X, so that the resulting, the induced embedding from F from A to the renormed X is an actual embedding. And furthermore, if your A and X are in K prime, then this renormed X is also in K prime. We actually make that happen. So we're going to construct our lattice now. So let's start with a countable set of embedding prime, and it's dense in the following sense. If you have, for some reason, so it's dense in the following sense for all embeddings between finite dimensional lattices, and for all epsilon greater than 0. There is some embedding U from A prime to B prime with your B prime and K prime that approximate both A and B and also approximate the embedding F. And we can do this by we can first go into some separable universal space, get some tuples, find some countable dense set of disjoint of finite dimensional lattices. And then for every epsilon greater than 0, we can approximate your A and B by some A prime and B prime, taking into account how they're how these are mapping into individual atoms and supporting them. And then we just let F be what U is, U be what F is, but then we're going to renorm that B prime so that we can get an actual embedding. And that's how you can get a countable set that is dense in this way. Also for X and K prime, we're going to let script LX be the set of all maps from some A prime into X, where A prime is the domain of some embedding in J0. And we can also have that V is a C embedding for some C greater than equal to 1. And you can also have a countable subset of L of X that's dense in a slightly different sense, that for all E greater than E prime greater than 0, and for all 1 plus epsilon prime, and for any 1 plus epsilon prime embedding from F from A prime into X with A prime in the domain of some embedding in G0, there is some 1 plus epsilon embedding from A prime into X, such that it approximates the embedding, the 1 plus epsilon prime embedding F, and it is also very close to F. So now we're going to do the construction. So start with x0 equal to x, and we're assuming x is in K prime. Suppose now that xk has been defined for all k less than or equal to n. We're going to let Ln be a countable subset of Lxn in the way that we described for L0 and L of x. And we're going to let gamma n be a collection of tuples in J0 times Ln that share the same domain. And then we're going to enumerate these for each gamma n. So basically, we're going to be applying amalgamation several times, and in particular, a sort of tweaking of an amalgamation property such that when you have your C embeddings, you have C embeddings from E to each of I, we can amalgamate, and then in such a way that one of your embeddings is a full embedding, and the other embedding just takes in all of the distortion from both of the maps. And we can also ensure that your G is in K prime as well, if your EF1 and F2 are in K. So now given your Xn, let's construct Xn plus 1 in your K prime, and we apply this corollary 21 over the nth pair of embeddings in gamma k for each k less than or equal to n, and then we're also going to amalgamate over all of the n pairs in gamma n. And so you get this repeated amalgamation process. So these stars are just kind of these increasing lattices up to Xn plus 1, and your straight horizontal lines are themselves full embeddings. These slanted lines are your C1, C2 embeddings, they are C1 embeddings because these U1Ns are themselves full embeddings. But again, all of the distortion is transferred away from the increasing sequence. But this distortion is going to become increasingly small because for many of these embeddings, because our C can be arbitrarily small. So you then get a sequence of xn's of increasing lattices. Take the inductive limit. It is of approximately universal disposition. We can show that with some diagram chasing and approximation arguments. And since our lattices xn were themselves finite dimensional, you have a finitely branchable such lattice. And so by our previous theorem, this is isometric to BL. So that's our construction. And that is the end of my talk. So.
All right. Thank you so much, Mary. Are there any questions or comments?
I have a question. In your construction of the amalgamation property, do you actually get that for any two lattice homomorphisms from E into F1 and F2, you get a push out of the diagram?
No, I was not able to show that there is a push out. I know that that Aviles and Tradesete were able to get the push out though. For mine, it was just the amalgamation. Okay,
so yeah. Yeah, once you get the push out, you get the amalgamation, but it's not clear how to go the other way. It doesn't always work the other way.
Right.
Oh, they did it in their paper? They did it in their paper?
Yes, I think so. I mean, they could clarify that, but I think they did, yeah.
Yes, we did, yeah. That's right. You can do the push out starting from two Banach lattices. That's correct.
Yeah, I do have a question as well. Thank you for your great talk. So I know if it's a question for you or for Pedro. So you mentioned their results with free Banach lattices. I was wondering whether the spaces which appear in your skeleton, do they have a special meaning or significance in the theory of free Banach lattices?
oh, I don't know about how they relate to free Banach lattices. I know that they work in a way that seems to be similar to the L infinity spaces for Banach spaces, but maybe Pedro can talk a bit about if they relate to free Banach lattices.
Yeah, sorry. So I think, I don't know exactly what are these lattices you are mentioning, Valentin, but yes.
I meant the L infinity n of L1m.
Right, no. So I don't know about the free Banach lattices of those. Our use of the free Banach lattice is to produce the push out. So essentially, you have to take, if you start with 2 Banach lattices, you take the free Banach lattice generated by the sum, and then you have to make a certain quotient to make sure that you don't get extra stuff. So maybe that's the connection with free Banach lattices. I mean, at least the one I know at this point.
What might be
I was thinking that maybe this construction would simplify if you are working specifically with those or something like that. I don't know.
What might be relevant is that the finite dimensional L infinity of L1s are injective Banach lattices.
I'm sorry, say again?
The finite dimensional L infinity of L1s are injective Banach lattices, just like the finite dimensional L infinities are injective Banach spaces.
Yes, I think that's the case with if you have L infinity, L1 spaces, and then the L1s are varying in length, right?
Yes. Well, yeah.
Mm-hmm.
So, yes.
But I think they are injective for the positive operators, right?
Yeah, as
so
Banach
as Banach lattices and taking the maps as just positive operators, not for lattice homomorphisms. For lattice homomorphisms, of course we don't have any injective objects.
Okay, are there any comments or questions? All right, if not, thank you so much, Maria Angelica, for a beautiful talk. All right.